As can be seen from the traditional construction practice diagram here, it may result in a fragmented nature as the different parties are working within their own silos. The contractor may not be involved in the design, despite being able to bring foresight and practicality to the final design. The traditional process may result in cost overruns and variations, which may therefore impact on the quality of the final product. It may also result in potential delays. The primary concern with the traditional form of construction is the loss of data. As different construction stakeholders are involved at different times, this communication and data capture becomes quite fragmented. Also, the use of non-environmentally friendly shipping methods, such as printing drawings and sending them over for review, driving to and from meetings, can also impact on a number of important environmental factors. In order to understand the importance of data capture, as well as some of the barriers that this encounters during the traditional construction practice, we will now look at this in more detail. The diagram here is represented as an explanation of how data is lost during the traditional construction process compared to how it can be gathered during the BIM lifecycle. The green line in the diagram represents the traditional way we capture data in a project. There are highs and lows. The highs represent when the required project stakeholders are working collaboratively together at the same time on the project. As with the traditional way of construction, each stakeholder has a specific responsibility, and when they complete this and hand over to the next trade subcontractor, they may then potentially leave the site and communication then lapses. This can result in data loss as well as poor communication, and this data may never be recovered again. Also, through the use of different softwares, there are interoperability concerns, which means that one software may not be able to process another software's capabilities, and therefore there is important data loss in the exchange of these softwares. Data interoperability addresses the ability of systems and services to create, exchange, and consume data. There is a need for clear expectations for the contents, context, and meaning of that data. The National Institute of Standards and Technology suggests that inadequate interoperability of buildings has resulted in $15.8 billion annual costs within the US. The red line represents a more focused and collaborative solution to collecting data, which is facilitated through building information modeling. The traditional approach, where only the most critical of data was stored for the minimum time necessary, is no longer acceptable. The data from the BIM process is stored in the model and can be used by different members of the design team to help with their deliverable. So just to recap, some of the common concerns with the traditional construction process include adversarial and fragmented processes. This is a result of different stakeholders working to deliver their part of the project, and they may not be aware of other deliverables and data associated with those deliverables. Due to variations and cost overruns, it may create an adversarial and fragmented environment. Little time spent at the design development. Due to the expense associated with the design, it can be difficult to explore variations due to the cost to do so. Poor site construction planning. It can be difficult to plan activities on site through 2D drawings, and therefore sometimes design intent is not fully understood, as well as little time spent in energy assessment or impact. The use of sophisticated energy analysis tools would not be common during the traditional process, as a number of variables are required, such as materials and orientation, in order to fully understand how energy analysis can play a key role. This is where building information modeling can play a key role, as the model itself can be used to advance this process. An interesting fact is that any improvement in productivity and successful adoption of modern innovative processes will have a major impact. For example, a 1% rise in productivity worldwide could save $100 billion a year, according to the World Economic Forum. So if we look at this from a smaller scale, by using innovative processes such as BIM, augmented reality, virtual reality, modular construction, amongst others, on a school project worth $2.5 million, we could easily save $25,000 by applying these innovative products. As we have highlighted, there are a number of concerns with the traditional construction progress. So what we will do is we will look at these in more detail, and importantly, we will examine how building information modelling can be used to address a number of these concerns. First concern is adversarial and fragmented process. The construction industry is often described as being adversarial. That is, it frequently involves conflict, opposition, confrontation, dispute, and sometimes even hostility. So how can BIM help with this? Well, BIM technologies can foster a more rewarding collaboration process, as the design team can work from a synchronized model within a common data environment in the sharing and recording of information. Markups can be formed online, and design changes can be implemented faster. BIM not only allows design and construction teams to work more efficiently, but allows them to capture the data they create during this process, which can be used to inform operations and maintenance activities. This information provides a historical database for the asset, which can be used to inform the client's facilities management team. BIM can also be used for clash avoidance. Potential issues can be highlighted before they happen on site, therefore removing potential confrontation. Access to a common data environment through the cloud will also mean that the team can have access to real-time information. Another problem discussed is that there is little time spent on design development. The diagram here is called the McLeamy curve. The McLeamy curve diagram highlights that the further you are through the design process, the higher the cost of the design change. This also has a direct correlation with potential project delays, wastage, and increased delivery cost. For this reason, the BIM process draws the project stakeholders together earlier so that the individual parties can coordinate their design input, encouraging a more integrated approach to project design and delivery. Shifting design effort forwards is for the benefit of the design. BIM provides an opportunity for the different stakeholders to evaluate possible solutions and identify potential problems of the final product before the start of actual construction. Software shown below is called Autodesk Insight and enables hundreds of designs to be completed by manipulating certain project parameters such as building orientation, building form, glazing requirements, amongst others. This information can be partnered with energy data to help the client select the most advantageous solution. This can give the client countless design alternatives and possibilities. The building is effectively designed twice, once in a safe virtual environment where a number of what-if scenarios can be applied before being built out on site. Poor site construction planning. This can result in unneedful waste, and this has had a severe impact on the construction sector. About 40% of solid waste in the United States derives from construction and demolition. Throughout the world, such waste involves a significant loss of valuable materials, minerals, and organic materials. It's also important to include other wastes such as time and energy. As for energy use, buildings are responsible for 20 to 40% of the global total, therefore contributing hugely to the release of carbon dioxide. With a growing population and reduction of natural resources, it's key that waste be kept to a minimum and we embrace more beneficial and substantial methods such as building information modelling, amongst other digital innovations. So how can BIM help in regards to waste management? The model can help with advanced material management techniques. The 3D model can be used to view what materials are inside, where they are located, and when they were ordered. The model, in partnership with BIM Principles, can be used to order materials just in time to ensure that no excess materials are ordered or there are no materials on site that are not required. Clash detection. A clash occurs when components that make up a built asset are not spatially coordinated and conflict. In a BIM process, these clashes can be spotted more easily during the design phase of a project ahead of work starting on site. This, with regards to traffic analysis, the model can be used to view site constraints, perform detailed traffic patterns analysis to understand the best route, therefore providing minimum impact on surroundings. What if scenarios can be performed to ensure that a number of actions are trialed before they are realized out in site and causing potential impact. Data can be streamlined, and this data is available in real time, and everyone can be ensured they are working from the most up-to-date drawings, therefore reducing mistakes and reducing rework. One of the key concerns with the construction industry at present is due to the huge demand to reduce energy and look for more sustainable practices. The construction sector is now responsible for 1/3 of global carbon emissions, 1/3 of global resource consumption, 40% of the world's energy consumption, 40% of global waste generated, and 25% of the world's total water consumption. Increasing energy efficiency and reducing energy consumption are some of the leading research objectives in the construction industry and have been backed by international strategies such as the 2020 Climate and Energy Package, which aims for a 20% increase in energy efficiency and a 20% reduction in CO2 emissions. The requirement now for the construction industry to reach these European targets while also reducing significantly energy consumption is more paramount now than ever. And that's why building information modelling has the opportunity to be partnered with energy analysis tools to really focus on this. BIM-based energy modelling provides several benefits, including more accurate and complete energy performance analysis in early design stages, improved life cycle cost analysis, and more opportunities for monitoring actual building performance during the operation phase. Specifically, a BIM model in partnership with a energy analysis tools can help rapidly produce energy outputs that are now being used to meet international energy standards, can calculate a full carbon footprint, measure heat flow, weight loss, dimension change, or mechanical properties as a function of temperature, calculate the building energy use and operating costs, which are based on the effects and the interactions of building form, materials, system, usage, and climate, estimate water use based on building type and number of occupants, and evaluate the effectiveness of alternative measures to reduce water use, calculate reasonable energy cost projections used for design decisions and financial analysis, understanding of how the application of renewable resource materials can reduce energy concerns, analyse every exterior surface of the building, including roofs, walls, and windows, for estimated potential to generate electricity, calculate the potential air tightness of a building, determine the most suitable orientation of the building for an architect or an engineer, as well as the shading percentages, as well as calculating each room's daylighting factor. This brings us to the end of segment 1 of 3 for learning outcome 1.3 in the BIM Principles training unit. A case study has been provided on the BIM Cert platform. This case study investigates the traditional construction process compared to the BIM process and focuses on a company's journey of moving from traditional construction to a more BIM related practice.